Okay, let's do an example with impulse momentum. So let's just take a look at the examples that are in the notes for Chapter 9. And our first example has a hockey puck, a hockey stick hitting a hockey puck. So we have a 0.5 kilogram hockey puck. It's sliding to the right at 10 meters per second. So I'm going to put a little subscript I. It's 10 meters per second to the right, and there's the little hockey puck. And it is hit with a hockey stick that exerts the force shown. And this is slide 37 of the Chapter 9 online notes, if you want to see a better drawing of the force as a function of time in milliseconds. And it looks like this. It sort of starts at 10, goes up to about 50 newtons, goes back down to 0 by 30 milliseconds. And the question is, what is the final speed of the hockey puck? Okay, we're given the mass of the hockey puck. Let me write that better. 0.5 kilogram hockey puck. We're given that mass. We're given an initial velocity. We're told that there's a force exerted over it on some period of time, and we're asked the final speed of the hockey puck. So we can use the impulse momentum theorem that the impulse applied to the hockey puck is equal to the change in momentum. So here's our sort of basic physical principle. And remember, this is just like when we use Newton's second law or when we use conservation of energy. We are starting with an equation that is a mathematical description of a general physical principle. We are rarely using that equation to plug numbers into one side and get the answer to the other. This is just our sort of starting point of the language, the mathematical language of the problem, and we're now going to take this general statement and put in the particular details for the problem that we're looking at, and then we're going to be able to expand it out to this particular problem and then look for what we need to solve. So what is impulse? It is an average force times the time period that force is acting. And the change in momentum, I've just got one object in this particular case. I could have a problem where there's 50 things flying around and I have to add up the momentum of all of those things. In this case, I just have to look at the momentum of the hockey puck. So the change in momentum is mv final minus mv initial. The mass doesn't change. There are problems that we won't have to worry about where you're looking at a rocket and the mass of a rocket changes because as it burns its fuel, the exhaust goes out the bottom of the rocket and there's not as much mass in the rocket anymore. So the change in momentum would also have a delta m. But in this case, it's just the delta v. There's only a change in the velocity. So this is delta p. So what I've done here is taken the general expression of conservation momentum in the impulse momentum theorem. I've written it more specifically. Now, what is the average force and the time period that the hockey stick is hitting this thing? And what are the signs? These are vector quantities. Well, our problem tells us that the puck is moving to the right. That's generally the positive direction. And our force on this graph is a positive number. That means that the impulse is in the same direction. The force is acting in the same direction that the puck is moving. So those numbers are all positive. I have VI is 10 meters per second. M is 0.5 kilograms. The time period over which that force is acting looks to me to be, well, it starts at 10 and it goes to 30. So that's 20 milliseconds. I wrote meters per second. It's 20 milliseconds, which is 0.02 seconds. And the average force over that period of time, well, the peak is 50. And this has got the curve. I didn't draw it very well. You can look at the slide. We're going to approximate that the average value is half of the maximum because it's roughly triangular shaped. So we're going to say that it's about 25 newtons. And that gives us then 25 newtons times 0.02 seconds is equal to 0.5 times V final, that's the thing we're looking for, minus 0.5 times 10. Okay, so now we're done with the physics. We just have a simple algebra problem to solve. 25 times 0.02 is 50 times 0.01, which is 0.5, 0.5. Did I do that right? I think so. And equals 0.5 VF minus 0.5 times 10, which is 5. Add 5 to both sides, and I rearrange that. I get 0.5 VF equals 5.5. And that gives me VF equals 5.5 over 0.5, or VF equals 11 meters per second. So there was a positive force acting on it in the same direction that it was moving, so that it increased its speed a little bit. The new momentum of the object is 5.5 instead of 5 kilograms meters per second. Stupidly, there's not a special unit for momentum. It's got units of kilograms meters per second, and there's no special unit for it. We could call it a Caldwell. That'd be fine with that, but it's just kilograms meters per second. So this was not a very significant change in the momentum of this particular hockey puck, but that's a simple application of the impulse momentum theorem.